Hi, welcome back. I am Naren, and in this video, we will be discussing about problem 4 of Google Kickstart 2022 practice session 3. And the problem is Sherlock and Watson gym secrets. This is the problem description, and we will make some notes from that. And the problem talks about gym buddies Watson and Sherlock, and there will be a gym trainer who will give three numbers A, B, and N to Watson and Sherlock. And after getting these numbers, Watson and Sherlock will pick two positive integers which are less than N, which is given by the gym trainer. And let's say these numbers are I picked by Watson and J picked by Sherlock. And the condition is I and J should be different. Watson, after picking I, will eat I power A number of sprouts per day, whereas Sherlock will eat, after picking J power B sprouts per day. And on any day when they eat I power A and J power B sprouts, you can try to calculate the total number of sprouts I power A plus J power B. And for a given integer k, if TS, this total number of sprouts, is divisible by k, then Watson and Sherlock think that they will get along well on that day. The problem is finding how many pairs of I and J exist such that I and J can take values from 1 to n, and also that I is not equal to J, so that given k, this I power A plus J power B is divisible by k. And since this can be a huge number, the final solution, the count that the problem expects, should be displayed as a modulo 10 power 9 plus 7. So the input for the problem is T for number of test cases, and for each test case we will get the input A, B, N and K. Output should be case hash T for test case number colon space and the final count that the problem expects, the number of I and J pairs that satisfy the condition. And about the limits, A and B can be up to 10 power 6, so we can use int 32. For K, it can be 10 power 5 int 32. For N, it can be 10 power 18, so we can use int 64. And the sample. So in the sample, there were 3 sample test cases. And if you look at the first one, which has A, B, N, K as 1, 1, 5, 3, that means A and B, that is I power A plus J power B, is what we are trying to calculate. Both A and B are 1, and I and J can take values from 1 to 5 because N is 5. And we are talking about modulo 3 because K is 3. And if you go through all the number of pairs I and J, that is 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, then 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, till 5, 1, 5, 2, 5, 3, 5, 4, 5, 5 are the I and J pairs. And for each pair I and J, you will sum it I plus J because A and B are 1. So if you sum it, you will also check whether it is divisible by 3 because that is the answer that we need to count. and if you start with 1 and 1, which will be 1 plus 1 2, it is not divisible by 3. Next is 1 plus 2 3, divisible by 3, so this is in the final answer. 1 plus 3 4, not divisible by 3. 1 plus 5 6, divisible by 3, so it is in the answer. 2 plus 1 is 3, it is included in the answer because divisible by 3. Then 2 plus 2 is 4, no. 2 plus 3 is 5, no. 2 plus 4 is 6, yes, in the answer. 2 plus 5 is 7, no. 3 plus 1 is 4, no. 3 plus 2 is 5, no. 3 plus 3 is 6, divisible by 3, but it is I equal to j, so we are not included in that, in this answer. So similarly, these are the numbers, the pairs I and j, for which the sum is divisible by 3. And if you count it, we have 8 such pairs. So the final answer is case #1 colon 8. Let's look at the code template. So we will read the number of test cases t, then we will go through each test case and read a, b, n, k. Let's the final answer be t pairs, which is initialized to 0, and we print t pairs. So this is the template code. Let's look at the algorithm. The algorithm for this problem is very simple. We will go through I and j from 1 to n, trying to process all the pairs I comma j. And for each value pair of I comma j, we will try to calculate I power a plus j power b modulo k. And we discard the case where I equals j, and we compute this for other pair. And if it results in value 0, then we count that in the final answer. So this is our take 1 for this problem. And the code for this, we have read a, b, n, k. T pairs will be the final answer. And we also have a mod const, which is 10 power 9 plus 7, because the final answer should be modulo this value. We go through I from 1 to n, and inside that we again go j from 1 to n. If I equals j, we skip. And for other cases, we find I power a plus j power b modulo k. And if it is 0, we increment the answer count with the modulo 10 power 9 plus 7. And then we print the result. Submit the code. Test run mode. 3 test cases. Running tests. Pending. It's completed, and the output 830, which is correct for sample output. Let's submit. For attempt 1, pending. Finished with wrong answer. So our attempt 1 resulted in wrong answer for test case 1 itself. Even though we have used int64 for all our variables, this I power a plus j power b can be a huge number, and which cannot be represented in int64. So we are dealing with number overflow, and also we are talking about modulo arithmetic. Hence we need to rethink about this solution. In modulo arithmetic, a plus b mod c is equivalent to a mod c plus b mod c mod c. So that is, if a and b are huge numbers, before summing it, we can apply mod c on each component to reduce the value before doing this summation and applying mod C later on. So we can try to apply this for this statement for our take 2. So when we apply that, our code will be, we will split each sum into different variable by applying mod k for even I power a and j power b individually. Then we will sum it applying the mod k. And we will try the take 2 with this modified code. And this also resulted in wrong answer. And for our test case 1, test set 1, for which we have got the wrong answer, we are dealing with I power a, where I is 10 power 3 and a can be 10 power 6. So that is, we are talking about 1000 raised to the power 1 million. But we are dealing with int64s, which can hold only around 10 power 18. So the numbers we are dealing with cannot be handled with int64. So our problem is reduced to finding I power a mod k, where I and a are very large and I power a value is more than the max that int64 can store. So as part of solving this problem, we are trying to narrow down, focusing on a different problem definition which deals with modulo arithmetic. And the new problem definition will be how efficiently we can calculate I power a mod k. And you can look at Stack Overflow to check how we can efficiently calculate I power a mod k. Note that while solving these kind of problems, if you have solved such problems before, you might be somewhat familiar with some of these concepts so that it can be easier or quicker to handle it as part of some programmatic like competitions. Otherwise, you can also explore through Google what are the concepts that you need to apply, but it will take a bit more time. So for the next step to improve the solution, we should also know about modular multiplication. A into b mod c can be a mod c multiplied by b mod c whole mod c. And also for modular exponentiation, I power a mod k is equivalent to applying I mod k first and raising it to power a and then applying mod k. And if we combine these two, we can write it as the I mod k to power a can be written as I mod k multiplied a times, then applying mod k. And this can be converted based on the first modular multiplication, and where we will multiply I mod k into I mod k, then apply mod k on the multiplied product, then again multiply by I mod k, again apply mod k on the produced product, and we can do this reduction by mod k on each multiplication to reduce the overall product value. And if you convert this into an algorithm, then let's say a1 can be this I mod k, and if you calculate this a1, then we multiply that a1 here to the result, which is initialized to 1, and we do this, and then we reduce the result by mod k here, and we loop through b times, which is here I power a, which is a times, because this code is a power b mod m taken from the Stack Overflow page. And if you write the code for this algorithm, so we will have small I as a1, which is a reduced smaller version of I by I mod k. Then we multiply, then the result will be adjusted I, which is 1, and then adjusted I will be multiplied by this small I, which is a1 in each instance of this iteration, and then that will be reduced by mod k, and we loop through to the exponent value, which is a, and we return that result. So this is our improved version for take 3. Let's submit the code. Submitting. Test 4 done. Submitting. Attempt 3 pending. It resulted in TLE. So this also resulted in failure for our test set 1, but previously it was failing with wrong answer because of the huge number, but we improved it by this better way to calculate I power a mod k, but now it is resulting in TLE, which is time limit exceeded. So we are dealing with a modulo arithmetic and trying to improve I power a mod k. The previous solution that we tried is still taking more time, so we need a better way to find I power a mod k. So there is something called exponentiation by squaring, where we can try right to left binary method to calculate this in a better way than our previous attempt. So that previously we were multiplying I mod k a times because it is raised to the power a. In the new solution that we'll attempt, where we will multiply only log a times instead of a times. If we have I power a mod k, we can split it up into I power a by 2 into I power a by 2 mod k. And this can be written as we have seen with modular multiplication, I power a by 2 mod k into I power a by 2 mod k whole mod k. If you take I mod k, we can multiply that by itself to get I mod k whole square. And to calculate I mod k whole power 4, we can just multiply I mod k whole square by itself to get I mod k 4 in a total of 3 multiplications. One multiplication to get whole square and another one by itself to get 4 instead of 4 multiplications of I mod k. So next we will multiply this by itself to get I mod k whole power 8. So in that way we reduce the multiplication count from a times to log a times. So this will be our take 4. So we change the algorithm slightly from the previous one, where we multiply each product by itself by raising a square, a to power 4, a power 8 by reducing it to by the modulo, and we reduce the exponent by 2 in each iteration. And to take care of the odd, we multiply the a1 to the final result. And if you write the code for this new algorithm, so it will look like this. with TA, which is like changed power exponent value A divided by 2 in each iteration, and calculating the I mod K, like rising its power in each iteration. Let's submit the code. Running tests. Completed test 5. Submit attempt 4 pending. Attempt 4 finished. Test set 1 pass, set test 2 TLE. And we scored 12 for test set 1, totaling 56 for session 3. So with our improved finding the I power A mod K solution, our test set 1 passed, whereas our test set 2 resulted in time limit exceeded error. And till now, we tried this as part of the attempts in the competition mode of the practice session 3. Whereas the rest of the attempts to solve this problem, we will try as part of the practice session after in the practice mode of the practice session, because of the time elapsement of the competition mode of the practice 3. So here we are talking about the limits for K and N. In test set 1, K was around 10 power 4 and N 10 power 3, for which our solution was fine. But for test set 2, we are dealing with K up to 10 power 5 and N up to 10 power 18. So where we are hitting TLE error. So if you look at our for loops, we are going from 1 to N for I and also J, where N can be 10 power 18. So how can we optimize this? So while finding our find mod, so we will write the new find mod 2. We also need to take care of the corner case when K equals 1. So we will add that also. If K equals 1, we need to return 0. And this is our take 5, and this also results in TLE for test set 2. For our take 6, we need to improve our find mod to find I power A mod K. So we will use find mod 2 for our take 6. And also, if you notice, for each I value, we are going through J from 1 to N, calculating both I power A and J power B. Whereas, even though I doesn't change in the J loop, we are continuously calculating repeatedly for each J value, which is unnecessary. So we can move it outside the J loop, since it is I power A mod K. Even this optimization results in TLE in take 6. So we need even more optimization. So now we come to take 7. So how can we improve this find mod 2, which is we are doing from for each I here, and find mod 2 for j to power b here. So note that here for each I we are going through j from 1 to n, calculating j power b mod k. When we change I while going through the I loop, we come again here and recalculate for all j 1 to n values, which is same even when I changes. So there is no need to go through finding j power b mod k again for each I. It is enough we calculate j power b mod k once from I to n and reuse it whenever I changes. So it's enough to calculate I power a mod k separately, j power b mod k separately, and then sum it when going through the loop. So we will just store it somewhere for both I power a mod k and j power b mod k, and we will just add it while going through this loop. So that is our take 7. So we will have two vectors of int64 I mod of n plus 1 will store I power a mod k, and this will store j power b mod k. And we can also do some more optimization to this. If you look at I power a mod k, j power I power, let's say you have I power a mod k and I power b mod k for I 1 to n. And let's take an example of I3 mod k and I5 mod k. We can write I power 5 mod k as I3 mod k and into I square mod k, mod of k. So that means if you have already computed I power 3 mod k, while calculating I power 5 mod k, no need to repeat for I power 3 mod k. We can reuse it from here and only calculate I power 2 mod k and then multiply it. So for I power a mod k and I power b mod k, we can calculate I power a mod k and then reuse it and multiply that with I power d mod k, where d will be b minus a. So similarly, other way around, if b is greater than a. So we can do this optimization while calculating or populating I mod and j mod vectors. So that's what we do. We calculate d equals b minus a and first find I power a mod k and then find I power d mod k and multiply that with already computed I power a mod k. This is one step optimization to populating these two vectors, just handling the other two cases. So this is our take 7, and now for test set 2, previously we were getting TLE, time limit exceeded, but now with this new solution it results in resource exceeded. Note that we are using vectors of int64, which is 8 bytes per entry, but we are dealing with n of 1080. So each entry is in the range of 10 power 18. Whereas the memory limit we have is total of 1 GB. which is 10 power 9. So we cannot store this kind of vector values under 1 GB. So hence we are hitting resource exceeded. So this solution, we cannot have a solution where we store this kind of data. So what is the next thinking process? We are having like order n of storage. Can we move to order of k? Because k is in the 10 power 5 order. So we can, if we have a solution where we can do with order power k, we can move from 10 power 18 to 10 power 5. And the order n solution that we looked at, we were calculating I power a mod k and I power b mod k for all I values between 1 and n. And we are doing the modulo k addition to check later on while counting. But note that our non-goal is finding I power a mod k plus j power b mod k values. We are not interested in the actual value of this equation as part of our solution. Because our goal as part of the problem is just to count I and j pairs such that this value is 0. So our goal is not to find values for all I and j for this equation. Our goal is to just count I and j pairs for which this value is 0. So we can try to improve the solution. So we want to calculate whether I power a mod k plus j power b mod k equals 0. Let's say we have 6 as I power a mod k plus 4 as j power b mod k and k as 10. So 6 plus 4 mod 10 is 0. And if you move 6 to the other side, 4 mod 10 is equivalent to minus 6 mod 10, which is nothing but adding 10, 10 minus 6 mod 10. So if we have m1 plus m2 mod k equals 0, like this equation, then m2 can be written as k minus m1 if m1 and m2 are less than or equal to k, our original equation, which is true because it is mod k. So when we have I power a mod k plus j power b mod k and mod k equals 0, we can treat them as this as m1, this as m2, where m1 plus m2 mod k is 0. So our new algorithm can be, so we will go through for each I from 1 to n. First we will find the m1, which is I power a mod k, and then we need to count how many m2 exists for j1 to n such that m2 equals k minus m1. And if we count that, we will add that count to the final. But the sub problem is, how can you count, given the m1, how can you count how many m2 exists for j1 to n with this condition where m2 is k minus m1? If we find a solution for this, we know that m2 is less than or equal to k. So instead of order of n storage, we can do with order of k storage. So now we will try to have a vector m where at m2 index in vector m, we will store the value, we will compute and store the value such that it will count number of j between 1 to n, for which j power b mod k will be m2. So we will go through j from 1 to n and we will find m2, which is j power b mod k, and if based on the m2 value, we will increment the value of m of m2, indicating there is one more j exists for which this value results in m2. So by going through j from 1 to n and calculating j power b mod k each time, we are maintaining and building a vector m such that each index indicating how many j exists, resulting in this value to be that index. So by going through j1 to n and computing this, we are creating information about the behavior of j, but using only a storage of order of k, because m2 is less than k. So we can write code as take 8 to compute this m. So we will define vector m of order k, and then we will go j from 1 to n, finding j power b mod k, which is m2, and we will just increment the m of m2 whenever we find value m2 for any j. So with this, we are building a vector of m such that we will know the count of all j's which can result in a value of m2 for any m2 from 0 to k minus 1. So our code is to compute this, count how many m2 exists for j1 to n, so which is in m of m2. So our algorithm is find m1, then get, since we have already built m, so just get m of m2, where m2 is k minus m1. So calculate m1, which is this, then just calculate m2, which is k minus this m1, and just get m of m2, so which we will increment or add to the final answer. So if we convert this into the code, we will go through I from 1 to n and find I power a mod k, which is our m1, and we will calculate m2, which is k minus m1, and then we will add m of m2 to the final answer. But there is a corner case when m1 equals 0, because then m2 equals k, which does not exist. So when m1 equals 0, m2 should not be k, but it should be 0, because k equals 0, it is a mod k. So this is our new algorithm that we implement. But we haven't taken care of the case of I not equal to j, which is a condition in the original problem. So how can we handle this? So that means when I equal to j, we should discard that value. But since we have already computed vector m and used for various I and j, we need to subtract some value to find out whether I equals j case is already computed in M of M2, which we have used to add in the final answer. If we have included that I equals j in this, then we will explicitly subtract that value from here. We know that M of M2 is counting all j such that j power b mod k equals M2. But for our final answer, j should not be equal to I. Let's find out whether what happens if j equal to I case was included here. If I equals j, then I mod I power b mod k should also be M. Because if I power b mod k is also M2 and j power b mod k is also M2, then it indicates that, because since this is part of this M of M2, it also indicates that we have included a case where I and j are equal. So we will calculate M3, which is I power b mod k, and we will check whether this M3 is equal to M2. If that is the case, then we will remove 1 from M of M2 while adding to the final answer. So to convert this into code, we will calculate M3, which is I power b mod k, and we want to check whether M3 equals M2, then we will minus 1. But we can also write it differently. Instead of writing M3 equals M2, we can write it as M3 equals k minus M1, or if you remove it here, M3 plus M1 mod k equal to 0. That's what we are checking as part of the take 8. And we also need to handle when a equals 0 case in the find mod 2, which should be 1 mod k. And when we try this with a sample test downloaded from the test set 2, which is available as part of the analysis page, where a and b are 0, but n is this huge number with k equals 1. This simple test fails with TLE for our new code. So it's still not able to compute this within the time limit. Note that from here we have moved to a M of k. So we have moved from order of n to order of k, which is 10 power 18 to 10 power 5 for vector m. And if you look at these loops, because we are now hitting time limit exceeded, this is going through 10 power 18 and this is also going through 10 power 18. Even though we have optimized this storage, we are still going through the loop for 10 power 18. So hence we are hitting TLE. So how can we reduce these iterations? We are going through n iterations while even populating M of M2. Can we reduce it? Let's redefine our vector M2, let's say L. So it remains same, that L of M2 is nothing but counting all j such that j power b mod k is M2 with j equals 1 to n. And we can write j power b mod k as j mod k to power b mod k as part of modular exponentiation. And when we go j from 1 to n, the j mod k will take value from 0 to k minus 1. So even though we go through j from 1 to n, this expression is taking a value of only 0 to k minus 1 to the power b mod k. Let's call this j mod k as q. Then when j takes values from 1 to n, q takes value from, say first it will take value from 1 to k minus 1 and 0 as j takes 1 to k. Then when j takes value k plus 1 and on, q will again go through 1 to k minus 1 and 0. So it keeps on repeating this. So q will take 0 to k minus 1, that is k values. We can rethink about this calculation of L vector. Instead of going through j from 1 to n, which looks like kind of a repetition here for each k, we can calculate this only once from taking j from 1 to k and compute the values. Then somehow, since it is a repetition, we can try to guess how many repetitions are there through some static formula and find that out to know overall, like q power b mod k we will calculate. Then we will try to find how many such q exists which can result in this value, like how many such q's exist when it takes value 1 and so on. So our new code will be, for calculating L, instead of going from 1 to n, we are going from 0 to k for q, and we will calculate q power b mod k, which is our m2. So we will increment L of m2, but we are doing this around n by k times, going through the same thing. So we need to add around n by k kind of a factor here, because it so much values will result in the same of m2. So we need to find out what is this number that we can add to L of m2. So this is part of take 9. So we are going q from 0 to k minus 1. m2 is q power b mod k, which is j mod k to power b mod k. So we need to increment L of m2 by, say, a value of y, where y is nothing but how many j we have such that j mod k is equal to q. So when j takes 1 to n, we calculate q equals j mod k, and then we need to know the possible values for j such that j mod k can be q. That's what we are trying to count. So if q, which is less than k, anyway results in q by q mod k, we know that if you add k again to q, which is q plus k, mod k is also q. Similarly, if you add 2k, 3k and so on, mod k of this value is also q. So we are trying to count how many such values exist such that adding some multiplier of k will result still in less than or equal to n. Let's say this is the maximum value q plus capital Q k. is the value which is maximum and less than or equal to n. Then the y that we need to count will be, there are capital Q number of numbers here that we are counting, and if you add one extra, that is Q plus 1 is our y that we need to increment. So by this number we know that Qk is less than or equal to n minus 2, and if you move k to the other side to find Q, then Q is floor of n minus q by k, and our y value is this Q plus 1. So while incrementing L of M2, we need to find floor of n minus q by k plus 1. If you convert this to code, the value we need to use here is floor of n minus q by k plus. So we have reduced, with this approach, we have reduced this loop instead of order n to order k iterations. But our I is still going from 1 to n, so how can we reduce it? So we have seen this approach for j by introducing q. Similarly, we can do for I by introducing p as I mod k and doing similar thing where I mod k can take 0 to k minus n values. So when I takes 1 to n, p takes 1 to k minus 1 and 0 and go on repeating. So p will take k values of 0 to k minus 1, and we will find p power a mod k and find out how many such p exists in I to n, which results in how many i's results in p as I mod k. And if we convert this into code, now our loop will be, instead of going from 1 to n for I, we are going p from 0 to k minus 1, and we find p power a mod k as m1, and the rest remains same, finding m2, and our final answer used to be adding L of m2, but now we need to take care of this repetition. How many such I results in p, which is in the order of n by k. So this is how we calculated floor of n minus q by k plus 1 for y, which is in the q case. If you repeat the same thing for p in our case, it looks similar, where we will use z in this case. Like, instead of adding L of m2 to the final answer, we need to add it so many times such that we have so many i's which results in p. So let's call it as z. And to find out that z, it is similar to our y, where we count how many such values in I exist which results in p for mod k. So we will have p plus 1 such numbers, where capital P is nothing but floor of n minus p by k, similar to what we did earlier. So we need to multiply this with L of m2 while adding it to the final answer. So if we convert this to the previous code, we will calculate z as floor of n minus p by k plus 1 and multiply z into L of m2 before adding to the final answer. And also, to discard I equals j case, we need to decrement it by z. And our attempt results in wrong answer. So how can we fix it? So we are using the floor here, and the floor approximations when the number is huge, like this one in our test case scenario, can result in minor approximations and change in the solution. So we should avoid floor in this case. And also, since we are talking about big numbers, we are trying to use this final mod constant only while implementing the final answer. We should try to use it at every level to reduce the overall size of the numbers and also to minimize any numeric overflows. And also note that we are adding this plus 1 for counting this case. But when q is 0, we should not count this one extra thing. So we should take care of that special case. So that is our take 10, where we have used this mod const everywhere, and we have removed the floor to directly use this value, which can downgrade that numeric result. And also, handling this q is greater than 0 only, then we will add this plus 1 extra, and here also for p. This attempt also results in wrong answer. So how can we debug this? Note that we are going q from 0 to k. We haven't taken care of the case where k is greater than n. So in which case we should not go till k, because we have to stop at n. And also, as part of some of these different takes, we have used int 16 for our mod 2 result, which is not sufficient. So if we fix them, we will have the condition when q hits n, so that means n is less than k, we should break this loop and stop for both p and q. And also we need to use int 64 everywhere. So that is our take 11. And the find mod 2 version that we are using currently for take 11 is this. Let's submit the code. Attempt 22 pending. Okay, test set 1 passed and test set 2 also passed. So that solved our problem finally. So now if we recap this whole attempt of solving the problem 4, what we have seen is, for new problem space, in this case it's the modular arithmetic used in this problem, we need more time to cover the basics if we haven't tried such problems before, because we need to think about optimizations with the knowledge that exists for that particular type of problem. So practicing such problems helps to getting more familiarity and also know more about the challenges in that space, so that you can handle such problems quickly in future. And this problem touched upon modular arithmetic, which has a use case to avoid numeric overflow, particularly in cryptography. And practicing problems helps in getting some familiarity and probable challenges in that space. So in this modular arithmetic, we have used these three formulas while solving this solution. And note that for some problems, the optimization itself is the actual solution. The simplest solution is very easy, which is a non-optimized solution. Just optimizing a simple problem itself is the main focus area of the problem definition. And always make sure you use big enough variables and handle corner cases. And as part of optimization, try to list all types of limits in the problem and then try to go from one limit to the next, from the largest towards smallest. And while doing it, think about reducing the space and the time complexity. By starting with the largest limit and exploring each next level. Like we started with n, which is 10 power 18, then we moved on to k, which is 10 power 5. So that is kind of an indication. So what the solution, expected solution can be. So since it is not working for the largest limit, maybe there is something which can work for the next lower limit. And most of the times when you reduce time complexity, you might increase the space complexity and vice versa. And also think about whether you can reduce some of the computing operations with formulas. Like if you are trying to find the sum of 1 plus 2 plus till n, instead of doing a sum in every step, adding 1 to 2, that to 3 to 4 till n, if you know that there is a formula exists that n into n plus 1 by 2 represents this sum, you can as well just compute this instead of going through these operations in a loop. So try to find such formulas while finding the solution for your problem. So if you find this useful, please like, subscribe and share, and thank you for watching.